So mathematically, the input is a vector. So the vector arrives to our neuron. So this one here. So we also have to take note that, like, going back to our previous video, we had that video where I was discussing how we can convert feature values into a feature vector. So feature values can be categorical, and we have to convert that into vectors. So we get for example, so a vector would be, a vector has d many dimensions, d dimensions. So the dimensions are determined by the features. And that will be our input vector. This is the signal or the input that arrives or that is sent to our neuron. So this one is a feature value for that feature or dimension. This is the second feature value for the second feature or dimension, and so forth. So the neuron stores d many weights. So for each feature or dimension, it is going to store the weight. So I'm going to take this opportunity to discuss what's the use of these weights. So again, if you're going to look back at our previous videos, we have learned that some features are useful and some features are not. So if you take a data set and you have a bunch of features there, not all of these features are going to be useful. And other features, there are also features that are really useful. Like, there will be a feature that will heavily influence the decision. And there are also like other features that we don't really care about that information, so it wouldn't influence our decision. So these weights here influence, or that is the level of influence of that specific feature. So if we see a weight that is really, really high, like let's say, at this point we're not really sure what a high value is, but let's just say, let's just put here infinity. Well, let's just think about weight which is like really, really high. So when the weight is really high, that would mean that the feature corresponding to that weight inflicts more influence than other features. So that feature would influence the decision, and particularly influences the decision to be positive, because it will make the activation more positive when it is high. But when it is also high, but on the negative side, the feature will influence the decision towards the negative activation. So let us say there are features, like let's say for example we have a problem that we want to answer or guess yes or no. So we have a question and the answer is yes or no. So we have a feature. Let's just take for example the question, would I like this specific subject? And like the question is like subject, would I like the subject? So what is the subject? Let's say the question now or the feature now is algorithms. So the value here is either 1 or 0, converting it to a vector. So is it algorithm? And we have found based on our data set that a subject being of an algorithm influences a lot to the majority of the data set. Like if it is algorithm, if it is true, then it is more likely that the student will like that subject. But if it is not algorithms, then students are not just interested with or to the subject. So this feature would have a higher value to the positive side, because if it is true, then it will influence the decision to be more positive than negative. And that's just the purpose of the weights. Some weights can also become 0 if they are useless. So yeah. So the sum is computed by this one, this formula here. So the activation is just the summation of the weighted sum. So each feature value here multiplied by its corresponding weight, and then all of those values here, so this is the weighted feature value, and then we add all of them up and we get the activation. So the activation is either positive or negative. So a bias is introduced to have a non-zero threshold. So it's just a fixed value we add to the previous value we have, or the previous formula we have here, just to have a non-zero threshold, because we don't want to get 0 values. Okay.